Good morning. Today I'm presenting our work on detecting speculative information flows. This is a joint work with Jose Morales and Andres Sanchez from India Software, Boris Kopp from Microsoft Research, and Jan Reinke from Saarland University. Speculative execution attacks such as Spectre exploit speculative execution, an optimization implemented in modern CPUs to leak sensitive information. So, how can we determine if a given program is secure when executed on a CPU that supports speculative execution? In this talk, I'm going to present a principled approach for reasoning about leaks introduced by speculative execution. Specifically, I will present the semantic notion of security against speculative execution attacks and their analysis to detect vulnerabilities. Let's start with some background on speculative execution. Speculative execution is an optimization technique whose goal is speeding up computation by avoiding idle times. In this talk, I focus on speculative execution over branch instructions. Note, however, that CPUs also speculate on other classes of instructions. Consider this simple program. Here, we check if X is in bound, and if that's the case, we perform two memory accesses. Executing the branch instruction requires to compare X and size. Instead of waiting for the result of the comparison to be available, the CPU queries a component called the branch predictor, which predicts the outcome of the comparison. Concretely, the prediction is based on the branch history and on the program structure. For instance, if the comparison is predicted as satisfied, the CPU continues the execution and performs the memory accesses. When the comparison's result is finally available, the CPU checks if the prediction was correct. If it was, great, we save some time by executing instructions in advance. Otherwise, the CPU discards the changes and restarts the computation. In more detail, changes to the CPU architectural state, which contains the register and memory, are rolled back. However, changes to the so-called microarchitectural state, like caches, are not rolled back. Now we have everything we need to understand speculative execution attacks. Here we focus on Spectre variant 1. The setting is the following. We have an honest process and the Spectre attacker. The attacker can trick the honest process into executing the snippet from before, encapsulated here into function f, with attacker-provided values. Observe also that the honest process and the attacker share the same cache. The goal of the Spectre attacker is learning the value of an arbitrary memory location into the honest process memory. Let's say that we want to learn the value of the location A of 128. Observe that A of 128 is not part of A, whose size is only 16. The attack works in four phases. First, the attacker trains the branch predictor to ensure that the condition is predicted as satisfied. Next, the attacker fills the cache with attacker's control data, depicted here in red. Then the real attack happens. The attacker tricks the honest process into executing the function f with 128 as input. Since we trained the predictor beforehand, the CPU executes the memory accesses, which leave a footprint in the cache. Specifically, the block containing b of a of 128 is loaded into the cache. Observe that the position of the gray block directly depends on the value of a of 128. Later, when the speculative execution terminates, the cache content persists, so the gray block stays there. Finally, in the last step of the attack, we can just extract the content of A of 128 by probing the cache and learning which of the red blocks has been evicted. So in the rest of the talk, I will present a principled approach for reasoning about these kind of leaks. The foundation of our approach is speculative non-interference, a novel notion of security against speculative execution attacks. In a nutshell, a program is speculatively non-interferent if it leaks the same information when being executed with and without speculative execution. Our framework consists of three main components: two semantics and an attacker model. The two semantics, a non-speculative one and the speculative one, model the program's behavior with and without speculative execution, while the attacker model formalizes the attacker's observational power. Let's look at the details. First, the non-speculative semantics is standard. Instructions are executed in order, one after the other. In contrast, the speculative semantics is novel and it captures the effects of speculative execution. Concretely, the semantics is parametric in a prediction oracle which abstracts away from specific branch prediction details. The semantics works as follows. Whenever we execute a branch instruction, the semantics queries the oracle which produces the prediction and the corresponding speculative window. That is, the number of steps that we should execute speculatively. Then, the semantics starts a so-called speculative transaction. When the speculative window reaches 0, the semantics checks the prediction. Speculative transactions are committed when the prediction is correct and rolled back otherwise. Regarding the attacker model, we consider an attacker that can observe the address of all memory accesses, the changes to the program counter, and the beginning and end of speculative execution. This is inspired by constant time requirements, which are a common way of characterizing side-channel free code in the absence of detailed microarchitectural models. So let's look at how this works with an example. This is the Spectre v1 snippet from before. We consider a case where x is out of bound and the condition is predicted as satisfied. So when executing the program under the speculative semantics, we start from the statement number 1. The semantics starts as speculative transactions and moves to statement 2 since the condition is predicted as satisfied, and the attacker observes this, denoted here by the start and PC2 observations. Then we speculatively execute the first memory access, and the attacker observes the address, in this case denoted by the load a plus x observation. Next, we execute the second memory access. Again, the attacker observes the address. And afterwards, we roll back the speculative transaction, discard all the changes and the programs to the program state, and jump to statement 4. Again, the attacker observes this, and finally, we terminate. We are now ready to formally define speculative non-interference. We say that the program P is speculatively non-interferent for a specific prediction oracle O if, for any two program states S and S prime, whenever executing the program P starting from S and S prime produces the same sequences of observations under the non-speculative semantics, then executing P must produce the same sequences of observations also under the speculative semantics. That is, speculative non-interference ensures that executing P under the speculative semantics does not leak more information than executing P without speculative execution. Observe that speculative non-interference is a non-interference style property where the non-speculative semantics describes what information we are allowed to leak. Finally, observe that speculative non-interference is parametric in the prediction oracle, which depends on the specific CPU branch prediction strategy. To overcome this limitation, in the paper we present a way of reasoning about arbitrary prediction oracles. Let's look again at the Spectre v1 snippet. Consider two initial configurations where x is 128, the size of A is 16, and A of 128 is 0 in one case and 1 in the other. Moreover, assume that the oracle predicts the condition as satisfied in both cases. Then, in both executions, we start the speculative transaction and we execute the memory accesses. The first memory access produces the same observations in the two executions. However, the second memory access results in different observations in the two executions. In one case, the attacker observes a load from the address b plus 0, while in the other, the attacker observes a load from the access b plus 1. Since these two executions have the same non-speculative behavior, these different observations result in a violation of speculative non-interference. So the Spectre v1 snippet is not speculatively non-interferent. Next, let's see how we can automatically detect this kind of leaks. Our approach for detecting speculative leaks works in two steps. First, we symbolically execute the program under the speculative semantics to derive a set of symbolic traces which summarize the program's leakage. Each symbolic trace consists of a path condition and of a sequence of observations along the path. Note that the observations can be produced during speculative execution, the red observations here in the picture, or non-speculatively, green observations. Next, we analyze the symbolic traces to detect possible leaks. Concretely, we analyze each symbolic trace. If we detect leaks caused by memory or control flow operations, we flag the program as insecure, and otherwise we flag the program as secure. In the following, I will give you some insights about how we detect leaks caused by memory operations. To be secure, a memory access executed speculatively must depend only on information disclosed through non-speculative observations. Given a symbolic trace tau, we encode the presence of memory leaks as a logical formula. The formula consists of three main components and it relies on a trick called self-composition. The formula states that we are looking for two program states such that, first, they both satisfy the path condition, that is, they are both represented by the symbolic trace tau. Next, the non-speculative observations are the same. This is obtained by requiring that the green observations must be equivalent for the two configurations. This ensures that the two states produce the same traces under the non-speculative semantics. And finally, we require that observations produced during speculative execution are different. Again, this is obtained by requiring that the red observations differ for the two program states. This ensures that the states produce different traces under the speculative semantics. So if this formula is satisfied, we actually have a counterexample to speculative non-interference, and therefore we found the leak. So to conclude, I would like to present Spectector, our tool for automatically proving speculative non-interference, and two case studies. We implemented our analysis in Spectector, a tool to automatically prove whether programs satisfy speculative non-interference. Spectector consists of a front end that translates x64 assembly programs into microassembly, an assembly-style intermediate language, and of a backend implementing the process that I mentioned before. Namely, the backend implements both the concolic execution engine for executing programs with respect to the speculative semantics and the checks for speculative leaks. The tool is implemented in the Chow Prolog language, and it relies on the Z3 SMT solver for symbolic reasoning. As a first case study, we used Spectector to analyze how compilers place spectra countermeasures. As a target, we analyzed 15 variants of the Spectra v1 snippet developed by Paul Cocker. We compiled these 15 programs with the Microsoft Visual C++, the Intel ICC, and the Clang compiler using different mitigations and optimization levels. As a result, we obtained a corpus of 240 assembly programs, and we used Spectector to prove security or detect leaks in each of these programs. This table illustrates the results. On the left, we have the 15 programs. On the top, we have the three compilers. VCC stands for the Microsoft compiler, ICC is the Intel compiler, and Clang is obviously the Clang compiler. We compiled the programs without countermeasures, with the automated insertion of fences, and for the Clang compiler with a countermeasure called speculative load hardening. And we also used two different optimization levels. So overall, we have 240 small programs. A black dot in the table means that Spectector proved that the program satisfies speculative non-interference, while a white dot means that Spectector successfully detected the leak. Let's look at the summary of the main results. First, Spectector detected leaks in all unprotected programs, except for one case where the compiler optimizes away the branch instruction, thereby removing all speculative behaviors. Next, we confirm all the vulnerabilities in the Microsoft compiler, which have been pointed out by Paul Cocker. For the automated insertion of fences, Spectector confirms that the ICC and Clang compilers produce secure programs, even though sometimes they introduce unnecessary fences. And finally, Spectector successfully proves that all programs patched with speculative load hardening are secure, except for two cases where we detect some minor leaks. As a second case study, we analyzed Spectector scalability. As a target, we used the codebase of the Xen hypervisor. We found several challenges in scaling Spectector to such a large codebase. Among them, the main challenges were first, obtaining realistic security policies, next, supporting a large fragment of the ISA, and finally, the path explosion problem due to inherent limitations of symbolic execution. To anyway run Spectector on the full Xen codebase, we made several trade-offs that affected our soundness and completeness. We have an in-depth discussion of these limitations in the paper. To evaluate Spectector scalability despite these limitations, we compared the time spent on checking speculative non-interference relatively to the time spent for discovering new symbolic paths. By analyzing paths of different lengths, we were able to evaluate the scalability of checking speculative non-interference relative to that of symbolic execution, and this factors out the path explosion problem from our analysis. Concretely, we analyzed 24,000 paths of at most 10,000 instructions each. This plot illustrates the results of our case study. On the x-axis, we have the time needed to check whether a symbolic trace violates speculative non-interference. In contrast, on the y-axis, we have the time needed to discover the symbolic path. Observe that both axes are log scale. Spectector relies on concolic execution rather than pure symbolic execution to discover paths, and this is reflected in the plot. Specifically, the dots in yellow represent the symbolic paths and traces derived without invoking the SMT solver, whereas those in blue denote the paths derived by calling the SMT solver. In this picture, diagonal lines represent 10x speedups. Observe that for 20% of the traces, checking speculative non-interference is between 1 and 2 orders of magnitude faster than discovering the corresponding symbolic path. For an additional 40% of the traces, checking speculative non-interference is between 0 and 1 orders of magnitude faster than discovering the path. For about 25% of the traces, checking speculative non-interference is between 0 and 1 orders of magnitude slower than discovering a new path. And finally, for about 10% of the traces, checking speculative non-interference is between 1 and 2 orders of magnitude slower than discovering a new path. Observe that most of these traces are associated with paths discovered without invoking the SNT solver, namely yellow dots. The bottom line is that our data indicates that the cost of checking speculative non-interference for a symbolic path is roughly comparable to that of discovering the symbolic path itself. Hence, our approach does not exhibit fundamental bottlenecks beyond those inherited by symbolic execution. So to conclude, I presented speculative non-interference, a semantic notion of security against speculative execution attacks. We developed a principled approach for detecting leaks based on symbolic execution, and we implemented our approach in a tool called Spectector, which we use to identify subtle leaks in how compilers place countermeasures against Spectre attacks. Additionally, we evaluated Spectector scalability on the Xen hypervisor codebase, and the main takeaway point of our scalability analysis is that checking speculative non-interference scales roughly as well as discovering new paths in symbolic execution. Spectector is available on GitHub, and see all the links and contact details here. Thanks.